we were talking about standard deviation. And so remember, standard deviation is really just a measure of the typical spread of a data set. So how far away from the mean most data values will lie. And so the bigger that standard deviation is, then the more spread out that data is. Now let me ask you this. If I took two different data sets, found the mean and the standard deviation of both of those data sets, could I then compare those two standard deviations? So for example, let's say I had a data set 1 had a mean of 5 and a standard deviation of 3. And let's say that one had 50 values in it. And data set 2 had a mean of 3 and a standard deviation of 1. And that data set had 10 values in it. Would it be fair for me to say that data set 2 is less spread out than data set 1? So let me ask you this. Can you compare apples and oranges? No. You can't compare apples and oranges, right? So can I compare two data sets like this? So the answer is no. We can't compare these two directly because they're from different samples, right? So we need a way that we can compare them. And so our answer to that is going to be the coefficient of variation. And so what coefficient of variation does is we're going to look at the standard deviation of a data set individually relative to its mean. And so we're going to say what percent of the mean is that standard deviation. So essentially we're going to take the sample piece out of it and we're going to make it into something unitless so that we can then compare across data sets. So let's say, for example, I didn't tell you, maybe I said that this data set 1 was measured in feet and data set 2 is measured in inches. But what coefficient of variation does is it eliminates units, it eliminates having to worry about the sample because we're going to be looking at it compared to its own mean. But it's going to convert it into something that we can compare across data sets regardless of how that data was measured. Because it's going to convert it to a percentage. So your formula for coefficient of variation, which we just call CV, it's the same formula regardless of if it's population or sample. It's the same formula, the only what we're calling stuff. So coefficient of variation is literally the standard deviation divided by the mean times 100. So we're converting it into percentages. So standard deviation divided by mean times 100. So by converting these to percentages, we're basically saying, okay, I'm going to turn those oranges and the apples both into pairs. And then we can compare pairs with other pairs. So that's what we're doing here. We're just converting everything into a percentage, eliminating any units that may have been the same or different to let us really be able to compare and say, now you can say without a doubt, this data set is more spread out relative to its mean than the other data set. All right, so here, for example, I've got a table that has heights in inches and weights in pounds of a basketball team. So if we just were to look at this data set, and I'll help you out a little bit. I'm not going to make you calculate this mean and this standard deviation of this data set by hand. So I'll go ahead and tell you. The mean weight, or the mean height, is 72.8 pounds, or sorry, inches. And the standard deviation of the height is 3.3 inches. And the mean weight is 187.8 pounds. And the standard deviation of the weight is 17.7 pounds. So just looking at that, would it make sense for us to say, okay, this is bigger, so it's more spread out? No, because pounds and inches aren't the same, right? Typically, pounds are going to be, if you can even compare a length with a weight, right? Chances are pounds are probably going to be bigger than inches, right? So it wouldn't make sense to compare these two as they are. So that's why we need that coefficient of variation, is we can look at it and convert it to a percentage relative to its own measurement, so relative to its own middle, and then say which one's effectively more spread out. So if we do that, so the coefficient of variation for height is always going to be standard deviation divided by mean, which usually means it's going to be the smaller number divided by the bigger number. Not always, but usually that's the case. Usually your standard deviation is not as large as your mean. So in this case, it's going to be the 3.3 inches divided by 72.8 inches times 100. So when we do that, what do you get in this case? So I'm just going to round to one decimal place. So 4.5%. So our height has a coefficient of variation of 4.5%. Or in other words, that standard deviation is 4.5% of your mean. That's what it's really saying. So then you do the same thing for your weights. So in this case, we can say without a doubt which one is more spread out relative to its mean. Which one? The weights. So in this case, weights are more varied, or they have more spread. It makes sense to say that now. So remember, anytime you're wanting to compare different data sets to see which one is more spread out, or thinking ahead to your next project, or a couple projects from now actually, thinking ahead to that, if you want to compare stocks to see which one might be a better option, then coefficient of variation is what you want to use to compare, because you want to look at it relative at the standard deviation relative to its own mean, and then compare across the different data sets. All right, so another way that we can compare across different data sets, and this is going to be by far the one that we're going to use more often in this class, is by using a standard score. So what a standard score does is we're going to figure out how many standard deviations away from the mean a data value is. So basically what we're going to do is we're going to use the standard deviations as a ruler. But because any data set can have any mean and any standard deviation, we want to kind of standardize that. So we want to put it all onto the same ruler, basically. So for example, instead of us measuring distances in inches, feet, miles, and then everywhere else in the world measuring distances in centimeters, meters, and kilometers, let's say we want to convert everything to be measured in terms of, I don't know, fathoms. So, or light years. We want to measure everything in terms of light years. Why? I don't know. But let's say, so basically we want to be able to put everything onto the same scale. And that's what the z-score does, or the standard score does for us. It lets us put everything onto the exact same scale. But realistically, what the z-score is it's just the number of standard deviations a data value is away from the mean. So what the sign of the z-score tells us, so it can either be positive or negative, or zero. So if your z-score is positive, the data value lies above the mean. If your z-score is negative, the data value is below the mean. What do you think it means if your z-score is 0? It is the mean. So if your z-score is 0, it is the mean because your data, so if it's the number of standard deviations away from the mean it is, if it's 0, then it's no standard deviations away from the mean, so your data value is the mean. So realistically, what we're doing is we're basically picking up every unit of measurement we can, or every data set with every single individual standard deviation and mean, and we're translating it down to a standardized data set that has a mean of 0 and a standard deviation of 1. That's what we're doing. And I'll talk more about what that process looks like in chapter 7. So I'll come back to that process then of what it looks like and why we're picking them up. But for now, just know the z-score is converting everything to the number of standard deviations away from the mean it is. So how do we calculate these z-scores? So if you have a population, your z-score is x minus mu over sigma. Keeping in mind x is what? X is your data value, right? Mu is the mean, and sigma is your standard deviation. So z is x minus mu over sigma for population. Guess what? For a sample, what do you think it's going to be? So basically what we're doing here is we're saying, okay, we're finding out that deviation, right? We're finding out how far away from the mean that individual data value is, and then dividing it by that standard deviation, or what a typical value is. So guess what? If you have a sample, your z-score is the data value x minus the mean x bar divided by your standard deviation s. So no matter what, you calculate z-scores the same way. It doesn't matter if it's population or sample. So regardless, the z-score is data value minus the mean divided by the standard deviation. So it doesn't matter if it's population or sample. You calculate it the same way. It's just like that coefficient of variation. The only thing different is what we're calling the pieces, what we're labeling them as. That's the only difference. But the nice thing is, by converting to these standard scores or z-scores, it actually lets you be able to compare across different distributions, because it's going to give you the position of a data value. So then you can say, okay, based on this position, there might be more space below it or more space above it. All right, so let's say I want to calculate a z-score. So let's say the mean score on the math section of the SAT is a 500 with a standard deviation of 150 points. So what would be the standard score or the z-score for someone who scored a 630? So no matter what, z is equal to the data value minus the mean divided by standard deviation. Now in this case, we can assume College Board knows the score of every single person who took the SAT, right? We can assume they know everybody's score. So we can assume this is population data, which is why I wrote it as z equals x minus mu over sigma instead of x minus x bar over s. But either way, it doesn't change how we calculate it, right? It's still data value minus mean divided by standard deviation. So what would my x value be here? What is my data value of interest? It's the 630, right? So x is always the one you're interested in. what would our mean be here? 500. And what's our standard deviation? 150. So we're just plugging those in. So 630 minus 500 divided by 50. Now, if you're going to plug this in all at once in your calculator, be very careful. If you're going to plug this in your calculator, you need to put parentheses around that numerator if you're going to do it all at once. So you'd want to put it in your calculator as in parentheses 630 minus 500 divided by 150. Otherwise, what your calculator is going to do, it's going to read it. If you don't put those parentheses in there, your calculator is going to read it like this: 600 minus 500 divided by 150. So your calculator is going to follow order of operations. So it's going to ignore that subtraction if you don't put parentheses around it. And so it's just going to do 500 over 150 first, and then subtract it from. So in this case, what do you get for your z-score? So z is 0.87. In this class, 99.999% of the time, round a z-score to 2 decimal places. There will be one exception to that rule, and I'll tell you that whenever we get there, but it's in chapter 8, I think it is. Chapter 7 or chapter 8. So there will be one exception, but otherwise we're always rounding z-scores to 2 decimal places. So I'm not going to tell you on the test what to round a z-score to. Always 2 decimal places. All right. So a quick way to check yourself, to ask yourself if your z-score is accurate. Most of the time, now this does not a always rule, but the majority of the time, your z-score is usually going to be somewhere between -3 and 3. Most of the time. It's not guaranteed. Your z-score can be any number. But most of the time, a z-score is going to be between -3 and 3. So what does this z-score tell us? We get a lot of information from this z-score. So what it means, so first look at your sign. In this case, is it positive or negative? It's positive. So that means whoever the student was who scored a 630, they were above the mean, or they were above the average. So if we had a picture of that distribution, and let's say here was our mean, we know this person is somewhere above that mean. So they're somewhere over here, right? And we actually know exactly how far over here they are. They're 0.87 standard deviations that way. So we're kind of using that standard deviation as a ruler. So let's say that I know one standard deviation is here. Then we know this person would be somewhere like right here. Right? So it lets us have an idea of where this person is. And I'll talk more about how you know where, we know how to find where the middle is, right? I'll talk more about how we know how to find where one standard deviation is, etc., on that later in the course. So I'm not going to make you worry about drawing these out right now. That's coming, don't worry. But we can use this to see, okay, where is somebody in our data set? But we can also use it to compare. So let's say that we have 2 friends who are in 2 different classes. So Jody got an 87 on her calculus test, and she was bragging to her best friend, hey, I did better than you. And the class had an 80 and a standard deviation of 5. And then her friend was disappointed because she got an 82, but the mean for her class was a 73 and a standard deviation of 6. So what we want to know is who really did better compared to the rest of their class, Jody or Ashley. So to figure that out, basically what you want to do is calculate the z-score for both of those. So for Jody, if we wanted to calculate that z-score, what would our x value be, or what would our data value be here? 87. Minus, what's the mean? And divided by what? Good. So if we calculate that, what is Jody's z-score? 1.4. Good. And then we do the same thing for Ashley. So Ashley got an 82. Her mean was 73 and a standard deviation of 6. So what do you get for Ashley's z-score? 1.5. So let me ask you this. Who did better compared to the rest of the class? Ashley did better, right? So kind of, for those of you who are picture people, the way to kind of think about this, so if the mean's here in the middle, and let's say 1.4 is here, 1.5 is here, think about, okay, who's higher up, right? Who has the bigger z-score? Because if we're talking about who, in this case, to do better, you want to be further above the class average, right? So you want to be further above that class average. So in other words, you want more space below you to have done better. So in this case, Ashley really did better.